So Bismillahir Rahmanir Rahim. Today we are going to start a new chapter which is about the work done and energies. So we start with the first topic, which is the work done. Work done. So in physics, the work is done when a body is moved from the one place to the other place when the force is applied. For example, we have a body here, and this is the initial, for example, this is lying on the ground, and this is the point A. So the body, we have a block, for example, this is lying at the point A, and a force is applied. So when a force F is applied on this object, and this object changes its position from point A to point B. For example, we have the same body, it is moved from this point to, we have the point B. We have the same object and the force is applied, and then displacement is covered. So we have this displacement. So this displacement is d. So whenever in physics, when a body, when a force is applied on an object and it covers some distance and it covers some displacement, in physics we say that the work is done. So mathematically, so we write W equals to the force multiplied by the work done, the displacement. So the displacement. So in physics, this is the definition of the work done. So graphically, so we have, for example, on the y-axis we have the force, and the x-axis we have the displacement. And for example, we have some amount of force. For example, this is 1, 2, 3, 4. So 4 newtons of force is applied, and the body covers, for example, 1, 2, 3, 4, 5. So 5 meters. So the displacement is in meters, and the force is in the unit of the unit is Newton here. So we have 5 meters is covered because of this 4 newtons of force. So we have, this is the work done. So the area under this curve is the work done. So this area is the work done. So this is how this is the mathematical form, and this is how we define the work done, we can say the graphically. So the work done, it is a scalar quantity. So we can see here, this is the dot product. So the dot product of the two vectors. So we have the force is a vector, and we have the displacement, which is a vector. For example, the force is applied, force is a directional quantity, and displacement is also a directional quantity. But whenever we take a dot product or the scalar product of two vectors, the resultant is always a scalar. Since this is a scalar, this can be larger than 0, it can be positive, it can be 0, and it can be negative. For example, if the force is applied on an object, and the displacement and the force are in the same direction, that means that the force is positive. And when the force is applied, for example, in this direction, and the displacement is vertical and the perpendicular to the force, that would mean that the work done is 0. Why? Because in the vector and the scalar product, we use the cos of theta, and we know that the cos of 90 degrees is 0. Another case, when we have the force, for example, that is applied in this direction, and the displacement is in completely opposite direction, means the angle is 180 degrees. In this case, the work done is negative. And the example for this one is the work done due to the frictional forces. Because if the object is moving in this direction, the displacement is in this direction, the frictional forces always opposes the motion. So the frictional force will be in the opposite direction. So the work done due to the frictional force, we can say that it's negative. So since it's a scalar quantity, it can be larger than 0, it can be equal to 0, it can be smaller than 0 or negative work done. Now this is the simple form. When the work done, the angle between the force and the displacement is 0, so we can simply write that the work done is the multiplication, simple multiplication of the force and the displacement. But what if we have a situation in which, for example, we have a trolley here, a force is applied in this direction, so this is the direction of the force, and the displacement is in this direction. So the displacement is in this direction, so we have this is on the ground, so we know, so we can see here that there is an angle between the displacement and we have between the force and the displacement. So how do we calculate the work done in this case? So in this case, what we need to do, we need to split the force into two components. This is what we did when we were talking about the vectors. So one component is here, so this is the y component, so this is the Fy, and here we have the Fx. Now, if we look at this situation, in this case, since the object is moving horizontally on the x-axis, the effective component is the Fx, and the Fy here, since the Fy is in the vertical in the y direction, so this force is not playing any role in this case. So we will take the Fx and then we will calculate the work done. So we can write the work done is equal to, in this case, is Fx dot. But we know that we can also write that the Fx is equal to cos of theta. So we have the Fx is the force multiplied by the cos of theta dot d. So we can write F d cos of theta, or we can just simply write that it is the dot product of the two vectors. So this is the dot product of two vectors. So here in this case we had the force and the displacement was in the same direction, so we just had to write the force multiplied by the displacement. But whenever we have the force and the displacement, they are not in the same direction, but there is an angle between the force and the displacement, then we use the concept of the dot product, and we use the F cos of theta, the effective. So here we discuss the work done by the constant force. So in this case, the force is constant. It means that the force was not changing. So that's why we just take the force and then we multiplied it with the displacement. So the force was not changing with time or the distance. So the force was the same throughout the time. And also it doesn't depend on the position. And now we want to discuss the work done. Work done by a variable force. So the work done by the variable force. So first we have to define what is the variable force. The variable force is that force which is not constant and is changing either with time, with the passage of time, or with the position, for example. So the first example is the gravitational force. For example, we have the earth here, So this is the Earth, and we know that the gravitational force depends on the distance from the Earth's center. For example, if we are on the surface of the Earth, the gravitational force is maximum on the surface of the Earth. But if we are moving away from the Earth's center, the gravitational force, the strength of the gravitational force will be decreasing with the distance. So it is not a constant force, but it is a variable force. And the example is the rocket. For example, we have a rocket, and that's moving away towards some satellite, or for example, if the rocket is going towards the moon. So the gravitational force that the rocket will feel because of the Earth will be decreasing when it's moving away from the Earth. So it is not the constant force, so it's a variable force. And the work done, since the force is decreasing when the rocket is moving away from the Earth, so the work done will also be decreasing. So another example is, for example, the magnetic force. So we have, for example, two magnets. So we have two magnets here, and they are this much apart. So we will feel some force, and when we bring these magnets closer to each other, the magnetic force will become stronger. And when the magnets are very much away from each other, for example, this much away from each other, the magnetic force will be relatively smaller. So the magnetic force is also a variable force. The other example is the electric force. For example, the electric force is also depending on the position. For example, if we are away from the charge, the electric force, the electrostatic force will be smaller. But when we are closer, when the test charge is close to the test charge, the two charges are close to each other, for example, positive and the negative charge, the force will be stronger. And here we will discuss a spring force, for example. So we have a spring. So this is a spring. So this is a spring, and here is the relaxed length. So relaxed length means that whenever we don't touch this spring, this will be the real length. So this is the relaxed length. So this is the relaxed length. But if we stretch this spring in this direction, for example, we will feel a restoring force in this direction. So we know that if we stretch it this much, the restoring force will be smaller. But if the stretching is more, then if we stretch too much, then the restoring force will be larger. And according to the Hooke's law, so we know that the Hooke's law, this restoring force is equal to minus kx, and the x is the stretching length, for example. So this is, for example, now here, so we have, this is the x. So this force, the restoring force of the spring, depends on the x. So it depends on this x. If the x is larger, the restoring force will be larger. If the x is smaller, the restoring force will be smaller. And if this x is 0, means if it's at the relaxed length, then there will be no restoring force. So in this case, so when we have the variable force, so in this case, how do we calculate the work done, since we are talking about the work done? So in the case of the variable force, what we do, we split the whole system into different small parts. So small parts. So we know that, so this is the, for example, force 1 here at this x. So we have the delta d1, small d. We have the, for example, here the small displacement we have, and this will force, and when we further increase the x here, so we will feel little bit stronger force, so we call it F2, and then we have the F3, and we have, for example, for F2 we have the small displacement 2, and then we have the displacement 3, and for the last one, for example, we call it the n. So n can be 3, 4, 5, so it can be any number, so n. So for the variable force, what we need to do, we first calculate the work done by this individual parts. So we calculate it individually, and then we sum all of them. We add all these work done, individual work done. So this will be, for example, the product of F1 multiplied by this small displacement will be the F work done 1, and then we will have the product of F2 multiplied by this part. So we will have, for example, this is work done 1, work done 2, and then we will have the work done n. So we will add all of them. So this way we will get the final total work done. So how do we do that? So we have the W1, for example, here. So we have this one. So we have the small, first we calculate 1. So we have the F1 and then the D1. If there is an angle, so we write the theta here. But in this case, we do not have the angle is 0, so this part is 0. So similarly, we will write W2. So we will have the F2 delta D2 cos of theta. So this is the cos of theta. So we have the work done 1, work done 2, and similarly we will have the work done n. So all of them we calculate individually. So we have this one. So this is here. And now what we do, so we just the total work done is equal to W1 plus W2, similarly Wn. So we write F1 cos of D1 plus F2, then we have so this can be D1 here, so we have the D2 cos of theta. So we sum all of them. So for the last one we write Fn, so delta Dn and cos of theta. So this is how we calculate the work done by a variable force. So this is the complicated or very long term we can see here expression. So to simplify the simplified, so we can also write this in a simple word. So the limiting case, so this delta is close to 0. Very close to 0 means we take very small parts. If we take very small parts and then we add all of them, so we will get the very accurate value for the total work done. So this is the summation symbol. So it starts from 1. So we have the 1 here, we have 1, and then we have 2, and it goes to n. So we write, so this is the I delta di again cos of theta. So what it means that, so we have the work done is the force multiplied by displacement, and if we have the angle, then we write a cos of theta. So this I means that the I starts from 1 to n. So we have the I starts from 1 to n. So this is the simple way to represent this complicated expression. So this is how we calculate the work done by the variable force. So the first example, similarly, so this was what I did for the spring force. So we just divide all this individual forces into small, extremely small distance displacement here. So the displacement, for example, here is close to 0. That means that we calculate the individual work done, and then we measure, and then we sum all of them. When we sum all of them, we add all of them, we will get the total work done. Similarly, in this case, we can also split this into small sections. So we will measure W1, W2, and then we go into Wn. So in this way, we will calculate the work done by the gravitational force, and then we can do the same thing. Similarly, we can do the same for the electric force, and if we can have any force that is variable, that is changing with the time. So this is how we calculate the work done by the variable force. If it's not constant, so we don't have any problem. We just measure, we calculate the work done by the individual small parts, and then we add all of them.